Okay, hello everybody, good evening. This is going to be a kind of GCSE and A-level live stream tonight. The first half an hour is going to be this kind of last minute panic GCSE revision. So do let me know in the chat if you are doing your exams tomorrow for GCSE. You've already done physics, or you've already done biology, you've already done chemistry. Hopefully they went okay. And now it's the time for the big guns to come out and to be doing physics. So tonight for the revision, I've got some questions. This one here is quite a nice tricky one. It has lots of different elements of the kind of physics together. I'm also going to go through what I think are some of the key points that you need to know about, just to remind you what you currently know. And then we're going to do some questions from an app called FizQuiz, just to kind of allow you to kind of have a go at, I guess, revising all parts of the course. So yeah. Hello everybody so far. So we've got James, Prem, Joe, Matty, Salah, Adil, Free Maths Lessons, Nathan, Joe. So lots of people here who've been in many live streams already. Of course, you can catch up with any of my previous live streams if you need that little bit of extra help, maybe later tonight, first thing tomorrow morning. So you can find all of those over at gcsephysicsonline.com. Also, I should say that I do have practice papers. This one here, the one we're going to be going through, is one of my own practice questions. In addition to all the kind of real past papers, I've got 12 papers that you can buy, 6 for paper 1, 6 for paper 2. That's 120 questions. And tonight, if you go to my online shop, which is physicsonline.shop, and you use the code 15, so FIFTEEN at checkout, that gives you an additional 15% off. If you do want to get some last minute paper 1s, or indeed get paper 2s ready for a couple of weeks' time. So I'm going to be doing GCSE content first. I think it says down here, I'm going to be doing GCSE from sort of 7:30 till 8. And then from 8 onwards, I'm going to be doing some A-level stuff until about 8:30. That's the plan. So the first thing I want to do is just go over some of the kind of key things that you need to remember. Let me just put the paper like this. I'm just going to zoom in slightly. Okay, so the first thing that I think you need to remember is that if we're looking at the mains supply, it's an alternating current and it's got a potential difference of 230 volts and it's got a frequency of 50 hertz. There we go. That is 1 mark given to you. Just remember that. It's 230 volts is the potential difference of the mains supply in the UK and it's 50 hertz. The other thing you need to remember is that if you have an ammeter, that's going to go in series with whichever component you're looking at. So an ammeter goes in series and a voltmeter goes in parallel. Okay, I think that's pretty much come up in every single past paper I've seen. Again, an easy mark for having ammeter in series, a voltmeter in parallel. And yeah, I think that's pretty much the two of the most important things that you need to think about. Also, if there are any 6 markers, don't forget that a 6-mark question is just the same as 3 2-mark questions. Okay, and 2-mark questions, not a problem. You don't really even have to think about them. Okay, so if you see a 6-marker, maybe for an experimental method, just think about breaking it down into maybe 3 smaller 2-mark questions in your head, and that means it's going to be much easier to approach it. What 6 markers are we predicting, Natalie? And is that Natalia? I don't know what 6 markers there could be. One that could be useful is, why do we use a transformer? Okay, that's probably more like a 3 or a 4 marker. So why do we use a transformer in the national grid? And the reason, this is probably more of like a 3-mark question, but basically what we do with a transformer is we increase the potential difference. That means the current decreases. And when you've got a smaller current, there's going to be a smaller heating effect, and therefore there's going to be less energy losses. Okay, and of course the national grid is a system of cables and wires that takes electricity from where it's generated to people's houses. Now, that one there is, I think, a paper 1 for AQA question, because it's not asking how the transformer works, it's asking about parts of the national grid, which is to do with the way that energy resources are used. So we've got like renewable, non-renewable, things that emit carbon or carbon dioxide more particularly. So yeah, this question here is more about the energy being transferred around the country and how we make that more efficient. So there we go. So yeah, although the transformers, the actual construction of them is paper 2, well, first of all, you've already learnt that anyway, but it's really about why we use them. And it's to increase the potential difference, which reduces the current, which means we're going to have less of a heating effect. And the reason is that power losses are equal to I squared R. And if we can reduce the current, maybe by a factor of 100, we then reduce the power losses by a factor of 100 times 100, so by 10,000. Hopefully that's helping. Okay, if you do have questions, I will be occasionally my eyes kind of like go all over the place because I'm looking at the chat as I'm doing the stream. Okay, so very quickly, I'm going to go through this question here. It's going to highlight some things. Yes, Anissa, maybe I could look at some of the practicals. Sorry, that's Temedola. Maybe I'll have a look at some of the practicals towards the end of the session. Now, the first thing is, in the exam tomorrow, there will be a difficult question. I've no doubt about it. And a lot of the time, you'll think, I've never learnt that before. But all the time, they will explain what's going on. So here we've got maybe something you haven't seen before. We've got a circuit over here designed to monitor the speed of rotation of a small fan with 2 blades. And the other thing is that if there's anything in bold, make sure that you identify and actually look at what that says. Sometimes it'll say to select 2 answers. Sometimes it says to give the answer to maybe 2 significant figures. Anything in bold, I would urge you, if you have a highlighter, to maybe just highlight that, or maybe underline it in a different colour so it's quite clear, because if they've put it in bold, it's there for a reason. Okay, so we've got a light that shines through the blade, and then we have this component over here. So the first thing is you need to be familiar with all your electrical components. This one over here is an LDR. It's a light-dependent resistor, and therefore its resistance is going to change with the light intensity. Okay, the output from the circuit is equal to the potential difference across the LDR, which is recorded on a voltmeter in parallel. The graph in figure 13 shows the variation of output with time. So what we can see is if we were to look at the reading on this voltmeter, over time it's quite low, then it goes high, then low, then high, then low, then high, then low. And this is because of that blade interrupting the light. So why does it have 2 distinct values of potential difference? So this question over here is relating this graph to this circuit in this setup. And as the blade rotates, a lot of the time, all of you will be getting easy marks just by stating obvious things. So we've got a blade which is rotating, and we can say as the blade rotates, it blocks the light. Okay, and it blocks the light for a short time. Okay, and of course, an LDR changes its resistance dependent on the light intensity. And the graph that you might be familiar with is one that looks like this. So we've got a graph of resistance against the light intensity. And what we see is when it's brighter, the resistance is lower. When it's darker, the resistance increases. And so for the LDR, its resistance increases when it's darker. Okay, and that increases the potential difference, because if you've got a higher value of resistance, we have a greater potential difference across that component, and this increases the resistance, or so this increases the potential difference across it. Okay, so a fairly wordy one over there. Okay, so there we go. For example, Hyperslane is saying like maybe when the blades are horizontal, it's blocking the light. Maybe a quarter of a rotation later, when the blades are in this position, all of that light is going to shine straight onto that. I suppose, why is it not a curved graph? I suppose potentially there might be a little bit of a curve down here and a little bit of a curve at the top. But this is like an ideal situation. It's basically the light is on or off. Okay, when the output voltage is at a maximum, a charge of 4 times 10 to the minus 6 coulombs flows through a 5 ms period. Calculate the resistance of the LDR at the maximum output voltage. So this question here, I think, would be the hardest kind of question you could possibly get at GCSE. So this is a multi-step thing. The first thing is, if you have a question like this in your exam, and you will have similar questions, is maybe underline or highlight the key data. So here we've got the charge, and that's Q, and it flows during a 5 millisecond period, so that's our time. And the other thing here is it's a millisecond, so it's a thousandth of a second. We want to calculate the resistance of the LDR at the maximum output potential difference. So the resistance is our unknown quantity, but we want to look at the maximum potential difference. So going back to the graph over here, we can see that the potential difference varies between 1 and 5. So reading back over to the axis, the maximum potential difference is equal to 5. So we can say that maybe V max is equal to 5.0 volts. Okay, so we've got V, T, Q, and we need to know R. Now, if we know V and we want to find R, we could probably use the equation that says V is equal to I times R. But we don't know I, it's not given to us. Instead, there is another equation that says Q is equal to I times T, and we know the charge, we know the time, and therefore we can use that to work out I, which we can then use in this calculation up here. So the way I found V was by looking back at the previous part of the question. And again, this is sometimes where they don't always give you all of the data in the question. Sometimes they refer to something which refers to maybe something explained at the start of the question. So this bit of stuff here came from the graph in figure 13. Okay, so we want to know I. I is equal to Q divided by T, and that's equal to 4.0 times 10 to the minus 6 divided by 5.0 times 10 to the minus 3. And the reason I'm doing 10 to the minus 3 is because up here we have a millisecond. So it's effectively saying 5 divided by 1,000. Okay, when we do that, I could probably do it in my head, but always rely on your calculator. This gives me an answer equal to 8.0 times 10 to the minus 4, and that's going to be amps. Okay, so we've worked out the current. Now we need to know R, so we're going to use this equation here and rearrange it to say that R is equal to V divided by I. Okay, now the potential difference is equal to 5.0 volts, so that's something we've got from the graph. And then this is the current up here, which is equal to 8.0 times 10 to the minus 4. And if I do that, this gives me an answer equal to 6,250. Okay, now that is an absolutely fine answer. If you put that for GCSE, you will get all the marks. I'm going to just give my final answer though as 6,300, because what I've done here is I've kind of rounded it up to the nearest 100, so that's a bit like 2 significant figures. Okay, so there we go. Yeah, right. So people are asking some good stuff. Prem says, should you write your 6 markers as full sentences or bullet points? I would say my personal preference would be to do them in bullet points. Okay, bullet points are fine as long as you have everything in a clear, logical format, you spell everything correctly, and you've covered all the bits needed. Bullet points will help you structure your answer, and it means that it's easier for you to check that you've got everything you need. Okay, how do you decide where to round to? I've given it to 2 significant figures here because we had 2 significant figures up here, 2 significant figures there, 2 significant figures there, so I gave my final answer to 2 significant figures. But at GCSE, this answer over here would be completely fine as well, and you'd get all the marks. Okay, I would say though, write down the equation, write down your working out, and that means if you do make a mistake, you don't lose 5 marks, you maybe just lose 1 or 2 marks. Okay, use figure 13 to determine the number of rotations per second of the fan. So for that one over here, this is where I think a lot of people might make a mistake. So it takes basically 20 milliseconds to go from 0 to a peak. However, there are 2 blades, and that's in bold for a reason. And that means in one rotation, it's going to break the light 2 times. So if we think about it, the time period is going to be equal to all of this distance here. So it's going to be 1 peak and 2 peak, and that's 1 rotation. And that means the time period is equal to 40 milliseconds. Okay, now this is then kind of a bit similar to maybe the topic you're going to do in the other paper looking at waves, but basically the time period is 40 milliseconds. Now the frequency is going to be equal to 1 divided by the time period, and that's 1 divided by the time in seconds, so that's 40 times 10 to the minus 3. And if we do that, that's 1 divided by 40 times 10 to the minus 3, which is equal to 25. So there are 25 rotations per second. Effectively, it's going at 25 hertz. And that's the way that we could actually record the speed of something going really quickly by looking at the graph that you might get with a data logger. Okay, so I reckon, my prediction is, there will not be a question as difficult as this in your real GCSE exam tomorrow. So if you can understand what I've been talking through, that means you're well on a good path to get the highest grade possible. Okay, somebody's asking about the graphs. So there are so many questions here. If it's a compare question, can you still bullet point? Yes, I believe that that would be absolutely fine, as long as you've actually compared the 2 things that they're asking you to compare. Okay, here are the graphs you need to know. So, first of all, for electricity, you need to know these graphs. Okay, these are the IV characteristics. You need to know these 3 off by heart. Okay, so we've got the IV characteristic for a filament lamp, which is this F or S shape. We have a fixed resistor, so that's got a constant resistance and it looks like this. And we've got a diode or even an LED, and it looks a bit like that. Now there's different symbols you can use for a diode, but it basically looks like that. Okay, so the other graph you need to know, there are 2 of them which are very similar. Okay, you've got a graph that looks like this and a graph that looks like this. Okay, this one over here has a resistance, and we can see how that changes with temperature. And this one has resistance, and over here we have the light intensity, often measured in lux. Okay, so this one over here is the graph of resistance for a thermistor because it changes with temperature. And this one over here is an LDR, which looks a bit like this, and that shows how as the light intensity increases, the resistance goes down. So these graphs here, you need to know about those. The other one you need to know about is actually pretty similar to this, and it's a graph that looks like this. And here we have either the activity or we have the number of radioactive isotopes, and we have time along the bottom. And if you want to work out the half-life of something, you just look at the original amount, you look at half the value, and then you go down, and this time down here is what we call the half-life. So I'm just going to call that T a half. And of course, if you then half that again, we then get to 2 times the half-life, and it basically halves and halves and halves and halves. Okay, I think those are the main graphs that you need to know. Can anybody recommend any more graphs you need to know for this part of the course? I know what there is. There is another one. This one over here is a nice one. Okay, this one here has a graph of the temperature of an object compared to the energy. Okay, now basically when you've got a gradient here, that's when we're looking at specific heat capacity, and we've got different phases. We might have a solid, a liquid and a gas, and as you increase the energy, we increase the temperature. But there's also going to be these points here. We've got a phase change as we have something turning from a solid to a liquid, so that's melting, and that's the specific latent heat of fusion. And then when you go from a liquid to a gas, we have the specific latent heat of vaporization when something is melting. And this is where you have a change in state. We increase the internal energy, but we don't increase the temperature. Okay, So I think those ones there are quite important. Any other things that we need? Oh yeah, of course, yeah. Here, the energy is going to break in the bonds. It increases the potential energy stored between those, but it doesn't increase the potential energy. In actual fact, the temperature is kind of related to the kinetic energy of the particles. Okay. I know some people here do have paper 3 quite soon, so good luck for those doing paper 3 A-level stuff. Yeah. Does ohmic mean directly proportional at a fixed temperature? Zeno, yeah. So ohmic, if you have an ohmic conductor, that means the potential difference is proportional to the current, and that's often at this constant temperature. Right. So I think those are basically the graphs that you need to remember for GCSE. Now, the next thing I want to talk about, and this is an app. I'm going to put it down here. The app is called Phys Quiz. Okay, I've been using it quite a lot. I think it's brilliant. And what we'll do is we'll do some questions. Okay, so we'll do some questions about isotopes actually, so I can explain it for a few people. Basically, an isotope is an atom that has the same number of protons but a different number of neutrons. Because it's got the same number of protons, it must be the same type of element. It will have the same number of electrons, and therefore its chemical behaviours will be the same, but it's just got a different stability to its nucleus. So this Phys Quiz, so I'm just trying to find out my phone. Where is it? Okay, so here it is. Right, Phys Quiz, GCSE Physics. We're going to do, I'm just going to put it out a bit so everybody can see what it's called. I know somebody in the chat's going to ask what it's called. It's on the App Store. We're going to launch. We're going to do some atomic structure. So let's do atoms and isotopes. If you'd like to play along at home, you can put A, B, C or D in the chat. So yeah, the astonishing discovery in the gold foil experiment was that A, B, C or D. Some particles were deflected back, most particles went through, some particles went through the foil, most particles deflected back. I would say the astonishing thing wasn't so much that it was empty. I reckon that is correct. And also most particles went through. So yeah, some particles were deflected back. And that's because there must be a positive nucleus deflecting that. That's tricky. In which way does the modern quantum model of the atom refine further the nuclear model? Okay, electrons are in fixed energy levels, or electrons orbit at fixed distances. Is it both 1 and 2? 1 and 2 are correct, 1 is correct, or 2 is correct. I'd say electrons, both 1 and 2 are correct. Okay, so we have different energy levels. Okay, the diameter of the atom is approximately, is it 10 to the minus 8, 10 to the minus 10, 10 to the minus 12, or 10 to the minus 6? I think, for this one over here, a lot of people are now putting 10 to the minus 10, so we've had Zeno saying that. We've got a range of answers. The answer is 10 to the minus 10. So the atom is about 10 to the minus 10. There we go. If an atom loses an electron, it becomes radioactive, positively charged, an isotope, or negatively charged. So for this one over here, if you lose an electron, people are saying BBB, positively charged. The answer is positively charged. Excellent stuff, well done. Okay, how many neutrons are in this atom? So let's see what the numbers people put down. How many electrons are in that? Oh, by the way, while you're doing this, if you want more questions tonight, go and buy my practice papers. Even if they're not for paper 1, they'll be useful for paper 2. Oh my God, there's so many people here saying 12. Adriel, Charlie, Zeno. Okay, there's so many people. Demida, Zena, Bramble. The answer is 12. Yes, nice. How many times smaller is a nucleus than an atom? Is it 100,000, 1,000, 100, or 10,000? So how many times smaller is a nucleus than an atom? I feel that this question may well come up tomorrow. Okay, so a lot of people are saying 1, 10,000. People are saying about 10,000. Okay, so if you think it's 10,000, you are correct. It's about 10,000 times smaller. Remember, 10,000. Basically, that's the answer. So let's just go to next. The Bohr model. Okay, right. Of these particles, which has no charge? An alpha particle, an ion, a beta particle, or a neutron? So, which of these, A, B, C, or D, or you can type it out, which of these has no charge? The answer, everybody's got this, you're all awesome, neutrons are neutral. What is the atomic number of this carbon atom? What is the atomic number? Is it 6, 14, 20, or 8? The atomic number is 6. Well done, people. Everybody's getting the correct answer there. Which particle determines which element an atom is? Okay, please don't spam, people. If you spam too much and put the same answer many times, I'll just time you out. Okay, so which particle determines which element an atom is? People are saying proton. There's so many people out there that I can't even read all of your names. But this is amazing. All of you are doing awesomely. What experiment led to the nuclear model of the atom? The nuclear model, of course, being the one where we have this central nucleus, which happens to be positive. And here, this is the experiment that all of you need to know about, the gold foil experiment. Correct. Okay, here we go. Electrons exist at different distances around a nucleus. They exist in groups of 2, in atomic order number, in groups of 8, or in energy levels. Okay, so in energy levels, and it's when they go from one energy level to another that we can maybe eject a photon. Okay, isotopes of an element have different numbers of, so if we've got the same element, but we've got an isotope of it, it will have the same number of protons and a different number of neutrons. Cool. If an electron in an atom drops to a lower energy level, it will do what? Will it emit electromagnetic radiation? Will it emit a neutron, absorb EM radiation, or emit a proton? So people are saying emits, A emits, Sala, Nathan, come on, one answer, Nathan. Hal, excellent. Everybody here is saying the first one. The atomic nucleus has the same number of protons as neutrons. Always, sometimes, or never. So the atomic nucleus has the same number of protons as neutrons. So here we have our nucleus. Is it the same? Is it different? Or does it depend? Sometimes. Yeah, things like oxygen, carbon-12, helium have the same number of protons and neutrons. What was fired at the gold foil in the famous gold foil experiment that Rutherford did? So what did we actually fire at that gold foil? People like Hyperslane, Sala, Joe, Anissa, Nathan, Christabel, John, Tosin. People are saying alpha particles. Yeah, there we go. New win streak. The electron is negatively charged. You know that. Should we do this for another couple of minutes? By the way, if you want to play this at home, I reckon you could do this for half an hour tonight and you would learn something. The discovery of the neutron in the nucleus was found by who? Okay, this one here is a little bit more tricky. Who discovered the neutron? So basically, J.J. Thomson was looking at electrons. Faraday was well before that. Bohr was maybe looking at electrons. People are talking about the Chadwick. So Chadwick was the guy who did that. Okay, the model of the atom which replaced the plum pudding model. So this is before the kind of the Bohr model. So which one replaced the plum pudding model? The answer was the nuclear model. Of these particles, which has a positive charge? So, which of these has a positive charge? This app's only for GCSE. I'm kind of working on an A-level app, but it's taking a lot longer than I thought. Proton, 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 proton. Proton is the correct answer. Now, I would say, if you want to have a go at this yourself, then make sure that you do go and look at Phys Quiz. Also, if you haven't already done so, make sure that you do go to my shop, physicsonline.shop. You can find some stuff there. I'm just going to see if anybody's actually bought papers during this live stream. It would be interesting to find out. because I know that a lot of people have been buying it with a 15% discount today. So we've got Praveen, fantastic, excellent stuff, getting the full AQA mega pack. We've also had people buying the A-level one, so some OCR practical packs being sold, which is awesome. So if you want to get this, you can maybe just get a couple of the paper ones, or you can obviously buy everything ready for paper 2, because now you know I'm here. You know I'm going to be doing live streams almost every day. You can find my schedule beneath this if you're a GCSE student. So my hair just stood up. Yeah, I will be doing plenty more GCSE Physics Paper 2 live streams over the coming weeks in the run-up to your final Paper 2 GCSE exam. Okay, yes, by the way, as Ritwik Gosain says, like the stream, it will give you good luck. So if everybody could like the stream now, I know there's lots of love there, then all of that will kind of help boost this. Right, that is the end of the GCSE stuff. If you want more GCSE help, go to GCSE Physics Online. It is now past 8 o'clock, and therefore we're going to be starting to do some A-level stuff. So thank you and good luck to all of you GCSE people. If you are an A-level student, do let me know in the chat at the moment, so I know I've got some A-level people here, as well as the GCSE lot, who I'm sure are going to go now. So for the A-level lot, thank you everybody, goodbye. A-level, we're going to be doing some questions. They are OCR questions, but they are suitable for all of you AQA, EdXL, EduCast, WJC, even the OCRB people. This stuff here is going to be suitable for anybody doing any A-level exams, because it's just the kind of generic skills that you need to know. Now, the only reason I'm doing OCR papers is because I don't want to get any copyright strikes from AQA. So let's have a look at some of these questions. Obviously, you can play along at home. I'm just going to get my work solutions. So a lot of these, again, just put down A, B, C or D. And of course, you might need a bit of scrap paper. So answer all the questions. I would say it does say in OCR, and I think it says in AQA as well, you know, there's about maybe 1.5 minutes per mark. If you find a question, you think it's too difficult, leave it and move on. Somebody's asking, are BPHO, the Physics Olympiad questions, good for revision? They are. I reckon if you're doing Physics Olympiad problems, the actual past papers will seem super easy by comparison. But it tests A-level skills at a high level of thinking. So if you want to get an A or an A star, then do Physics Olympiad problems. Okay, so what is a reasonable estimate for the kinetic energy of this athlete? So an athlete running at a speed of about 5 meters per second. So kinetic energy is equal to a half mv squared. I'm going to say that I'm a runner, but my mass is about 100, well, it's about 93 kilograms. And then we're going to multiply that by 5 squared. So that's equal to 50 times 25, which is equal to whatever that is. Is that about 1200? That's about 1250, which I would say is probably closest to that one over there. So I would say the answer, everybody's got it, is C. So we've got Blaze, 4, Joe, Boris, Sagiza, Charlie, Avish, Ollie, Myth Bell, Fern, Ritwick, Sagiza, Conalaven, Bramble, Uchicha, Itacha, Chloe, Jamil, Adam, KV, loads of people. Right, which pair of quantities have the same SI unit? Now for this, we know that force is measured in newtons and strain is dimensionless, so it can't be that one. Force is measured in newtons, stress is a bit like the force per unit area, and therefore it's got the units of pascals, so it's not that. Pressure, force per unit area, pascals, stress, force per unit area, that's the correct one. And of course, strain is unitless and upthrust is a force in newtons, so it can't be that one. So the answer for this is C. Good, everybody's getting this correct. This one here at the moment is now an A-level part of the stream. If you want to re-watch the GCSE one, you can do from earlier on. A tennis ball is hit with a racket. The force applied to the racket on the ball is F. The ball has a vertical path through the air. Which statement is correct when the ball's at its maximum height? Do not forget the basics, people. Draw a diagram. So that is the ball. At the maximum height, it's got 0 velocity because it's got to the highest point, but there's going to be a force down due to its weight. Okay, the ball has a downward acceleration. It does, because the resultant force on it is due to its weight and therefore it's down. So that's true. The force acting on the ball is F. Well, that's not true because that only happened when the ball was being hit by the racket. It experiences no drag because it's not moving, and there's no drag, so the weight can't be equal to it. So here the answer is A. So I would say for something like this, draw a diagram based on what's in the question, look through all the statements, and even though you know that A might be the correct statement, it's worth just checking through all the others as well. Great stuff, everybody. Okay, this one over here is a question, again, which I think is it's worth using a pencil, I think, for sometimes in case you make a mistake. So an oscillator is forced to oscillate at different frequencies. Here we've got the graph of amplitude against frequency. So what we need to think about is if the damping is now decreased. Now effectively the peak, if we think about where the peak goes, the peak follows a path that kind of goes up to the right a bit like that. Okay, and if we had something which had less damping, it would be freer to move, so therefore its maximum amplitude as it was oscillating at resonance would be bigger. And what we get is a graph that kind of sort of is going to be, the values are going to be sort of above this. We're going to go up to like a peak value up here, but it's like a thinner peak, and then it kind of drops down a bit like that. Okay, so basically this is with less damping. So how do we compare the red line to the black line? The amplitude of the oscillations at any frequency decreases. I would say that that's not true. So we're going to put a line through that. The maximum amplitude occurs at a lower frequency. Well, that's not true because it actually occurs at a higher frequency, and the peak on the graph becomes thinner. Now, even if you didn't know it, it must be this because these two here are definitely incorrect. So that is a correct statement, and therefore it can't be only 1, it can't be only 2, it can't be 1, 2 and 3, and that means 3 is the only correct statement, and therefore the answer is C. Okay, hopefully that's good. Yeah. Right, the gravitational force between 2 point masses is F1. Okay, so this question here, we know that the force is equal to GMM over R squared. Now between two objects X and Y, the force is F1. So F1 is going to be proportional to X times Y over the distance between them. Okay, the mass of X increases and the distance between X and Y is halved. So basically the value of X goes up and R is now going to be equal to R over 2, squared. So that means the new force is going to be proportional to a bigger value of X times Y over R squared over 2, which is proportional to XY over R squared, so it's 4XY. Okay, so I would say then that force 2 is going to be equal to, is going to be bigger, because XY over R squared is F1. Sorry, this is probably the worst way to show it, but basically force 2 is going to be bigger than 4 times F1. Okay, have I explained that well? Yeah, failed organ. Damping has come up in this paper only because it's an OCR question. It wouldn't necessarily come up in an AQA, so it's just worth checking. So this question here, I would say that B is the correct answer. Okay, the force isn't going to be smaller than the force at F1 because basically we've made the distance half as big, and therefore the size of the force, because it's a 1 over R squared relationship, is going to go up by at least 4. And because X is now bigger, then it must be bigger than 4 times F1. Okay, I've explained that pretty badly. Okay, right, here we go. The diagram below shows 2 energy levels for the electron in a hydrogen atom. The electron makes a transition shown by the arrow. What is the wavelength of the photon emitted? So I would say for this question here, don't look at the possible answers. If it's a calculation, don't look at any of them until you've actually worked out the answer yourself. So for this one, we know that the change in energy is equal to hc over lambda. We want to work out the wavelength. So the wavelength is equal to hc over the change in energy, which is equal to Planck's constant, which is 6.63 times 10 to the minus 34, times the speed of light, so 3 times 10 to the 8. And the change in energy is going to be equal to 5.44 minus 1.36 times 10 to the minus 19. Okay, so it's just a question. It just happens to be that this is a calculation question. Right. So if we put that into our calculator, this is equal to 487.5 Newton meters. Okay, so I worked that out. And that means, looking at this is the closest answer. So the answer is C. Okay, right, the next one I've seen come up quite a few times. Now, AQA people, ignore this. Just go and spend a minute looking at my website, looking at some other videos or something for a minute, or even look at my shop where you can buy paper 3As. People are asking, will I stream again on the 3rd? Yeah, if you want to see my streaming plan, I've got a bit of a break next week while I'm kind of sorting out my new office, which is going to be big, mega, big studio. It's going to be quite exciting, very expensive though, but yeah, I've got a big new studio I'm kind of building next week. So there's been no streaming next week, but the week after and the week after, I'll be streaming again, like 5 days a week, before paper 2 and before paper 3. Okay, so we're going to convert from kilometres per second into megaparsecs. So the value of Hubble's constant, if it's 73.5 kilometres per second per parsec, we times it by 1,000 to go to metres per second. We're then going to divide by megaparsecs. Now, you should have the conversion factor, which is given to you in the data book. Because it's a megaparsec, it's 10 to the 6 times bigger than a parsec, and that's therefore 3.09 times 10 to the 22 rather than 10 to the 16. And that gives an answer equal to 2.38 times 10 to the minus 18 seconds to the minus 1. Okay, and if we do that, that is answer B over here. And of course, the age of the universe is equal to 1 over the Hubble constant, if we've got our time in seconds. So if you did 1 divided by that, 1.238, 10 to the minus 18, that's going to be about 4.2 times 10 to the 17 years, which if you convert from seconds into years, 4.2 times 10 to the 17 seconds, which when you convert it into years is about 13 to 14 billion years. Okay, let's find an easier question for you to have a go at. Here we go, I like this one. So a wooden block is stationary on a ramp, as only happens in A-level physics classrooms. The diagram's not drawn to scale. Always worth checking for the bold text. That's something I talked about, and that's something that was identified in previous examiners' reports from last year. So the frictional force F is not shown. Which triangle of forces is correct? Well, there's going to be a weight acting down, so any of those could be correct. There's going to be a normal contact force acting up like this, so that's N. So N must be going like this, so it can't be that one, and it can't be that one. And there must then be a force which goes back to the starting point of that triangle. These are going to be at 90 degrees because we've got our force acting up here, F, and therefore the answer can't be A, it must be B. So we've got a triangle that ends at the beginning, and that means there's no resultant force. So we've got a complete triangle. So this one over here, the answer is B. Okay, right, I like these questions. Laser light of wavelength 640 Newton meters is instant normally on a diffraction grating. The separation between adjacent slits is 3.3 times 10 to the minus 6. What is the total number of bright spots that can be observed in the diffraction pattern? So don't forget, there's going to be a central maxima, and then there's going to be a certain number of fringes that go out in all directions, but the maximum angle must be when that's equal to 90 degrees. So effectively there could be a spot if the angle here is less than 90. So what we can say, so I'm going to check my working here, is that we know that n lambda is equal to d sine theta. We want to find the maximum value of n when theta is tending towards 90 degrees. And of course, sine of 90 is just equal to 1. So sine 90 is equal to 1. And therefore, we can say that n is equal to d over lambda. So we can put the numbers in, 3.3 times 10 to the minus 6 divided by 640 times 10 to the minus 9. And when we do that, we find this is equal to 5.15. Okay, so effectively, n has to be an integer, and therefore n is equal to 5. So we've got basically a central spot. We've got 5 to the left, and we've got 5 to the right, and that's equal to 11. Okay, so the answer is D. And I suspect lots of people have said n is 5, so you've got 5 to the left and 5 to the right. But you've got the 0th one in the middle as well. Okay, a spring is stretched by hanging it on a variable mass m. The mass is always at rest, the Springer-Base-Hooke's law. What's the relationship between the elastic potential energy and the mass? So for this, you could say that the elastic potential energy is equal to a half k x squared. Okay, what else do we know? We know that k is equal to the force divided by the extension, and the force acting on that spring is equal to the weight, which equals mg over x. So I'm going to put that back in there. Is that right? X. X is equal to mg over k. And if we put this back into there, excuse that bit, we know that EE is equal to a half k times mg squared over k squared. And therefore, the energy is going to be proportional to m squared. So it's going to be proportional to m squared, which in this case is d. Okay, how are people doing? Right. Yeah, I'm afraid, Tangier, somebody did put up a walkthrough of an AQA paper, but it got taken down by AQA, I'm afraid, because they, for some reason, they haven't released the 2023 papers yet this year. And I know they probably should have done. They normally do release last year's papers, but AQA haven't done it yet, and I can't release them because, you know, basically you're not allowed to do that. Okay, which of the following distances are largest? We've got this in meters, we've got that many parsecs, that many light years, and that many astronomical units. Again, this is something that you need to know the conversion factors, especially if you are OCR people or EdXL people. So basically, when we convert this from parsecs into light years, because we're multiplying by 3.09 times 10 to the 16, this is equal to about, so I've got the number here, 5.9 times 10 to the 16 meters. 3.42 light years is 3.2 times 10 to the 16 meters, and 593 astronomical units is about 8.9 times 10 to the 13. And therefore, the largest is this one over here, 5.9, which is B. Okay. Okay, everybody can do this one. This is an easier one. There's no maths involved. An oscillator is executing simple harmonic motion. Which graph of kinetic energy against displacement is correct for this oscillator? So basically, if something is, you know, it could be going side to side or up and down, it doesn't actually say. The kinetic energy is going to be maximum. So you're going to have KE max at V max, and the V max is going to be at x equals 0. So there must be the maximum kinetic energy in the middle. Okay, and of course kinetic energy is going to vary with time, so it can't be A, which is a constant kinetic energy, and it can't be this one down here. And then it's really a 50-50 choice. So the kinetic energy is going to be 0 at the extreme displacement, so where the amplitude is the maximum, or the displacement is the maximum. So it's either going to be this or this one, and I would say it's going to be B, because we don't just have this linear kind of line like this. Okay, all right. Here we go. Everybody loves an uncertainty. So the Young modulus of a metal can be determined using the expression E equals 4F over epsilon pi d squared. So here's some data. What's the percentage uncertainty in E? Well, the percentage uncertainty in E is going to be equal to the uncertainty in F plus the uncertainty in the strain plus 2 times the percentage uncertainty in the diameter of the wire. Okay, there we go. So we're going to have this here, which is 5.3. We're going to add that to the uncertainty in the strain of 1.2. And then we're going to add 2 times the uncertainty in D, so that's 2. So that's 5.3, 6.5, 7.5, 8.5. So I would say the answer for this is D. Well done, Chloe, Jack, Fern, Boris, Blaze, Daniel, Ben. Excellent work, everybody. Miss Katie Bell, of course. Yep, all of that is good. We then have a velocity against time graph for objects A, B, C and D. Which object travels the greatest distance between t equals 0 and t equals t? So if we want to know which has travelled the furthest, we know that the area underneath the VT graph is equal to the displacement. And therefore we need to think about which of these lines has the biggest area. So I would say, just by looking at this, and we're only going up to this line up here, I would say that underneath C, that looks massively bigger than the other areas. So I would say, just doing it by eye, I would say my answer is C. Of course, you can work it out, but I would say that this area C is so much bigger than the smaller triangle underneath B, or the even smaller triangle underneath the other one. So you can see that this kind of blue area is a lot smaller than the red area. Okay, and the final question today. This is nice. This one here is not correct. So, kinetic theory used for ideal gases. I know this probably comes up in maybe paper 2 AQA, is it? I can't remember. There are a number of assumptions. Which of these is not correct? The collisions of particles with each other and the container walls are perfectly inelastic. I would say that that's incorrect because the collisions are elastic, and that means kinetic energy is conserved. So I would say that that is the incorrect statement. The electrostatic forces are negligible except during collisions. That's correct. The particles occupy negligible volume. That's correct. There are a large number of particles in random motion. That's correct. And the incorrect one is A. And there we go. Hopefully that's all good. Right. I think we've kind of pretty much come to the end of the session. Does anybody have any easy, quick questions or anything they'd like a bit of guidance with? I think at the moment, all you can do now, basically, is spend the next 2 days just doing as many past papers as possible. But you do not need to write everything down. If you want to get through as many questions as possible, it is possible just to read through the question, maybe think about what the answer is, and just maybe have the mark scheme there with a bit of paper covering the other answers, and just think about, is the answer that you'd think, is that what's on the mark scheme? Of course, if it's a calculation, you need to do that. But sometimes you'd actually have to write everything down. I mean, writing stuff down is the best way of doing things to really learn deeply, but you might be able to cover twice as many past paper questions just by reading through a paper, looking at some work solutions potentially, and also just actually looking through the mark scheme. So that can kind of give you a lot more kind of a range of questions to look at. Okay, how many past papers a day is too much? I reckon 2 or 3 past papers a day is absolutely fine. What papers should you do if you've done all the OCR ones? I would say do some Edexcel ones if you've done the OCR ones. If a quantity like 4F from before is multiplied, does its percentage uncertainty stay the same? Joe Smith, yeah. So if you've got an uncertainty question where you're adding percentage uncertainties to find the total or combined uncertainty, if there's a number like 4 or there's a constant like pi, that has no uncertainty, and therefore that number doesn't add to the uncertainty in your calculated value. Key advice for securing an A star, Argon. Basically, it's just a case of doing lots of questions, and if you can, go harder than the past exam papers will be. So look at Isaac Physics, look at British Physics Olympiad questions, and if you work at that level, when you come back to doing past papers, they will all seem a lot more straightforward. Can you go from a B to an A in 2 days, Ollie? Of course you can. The difference between a B and A is marginal, and it might just be just getting your definitions under control so you know all of those. It might just be the exam technique of reading the question. It might just be a bit of good luck on the day. but you can definitely go from a B to an A in a couple of days. Right, Thinagen, would I recommend doing past papers or going over topic questions for specific topics coming up on the paper? I think, yeah, both are good options, but if you know there's one topic you really hate, it might be like electricity and you just don't like electrical questions, just do lots of those questions. Do the questions that you hate doing. I think that's the best thing. If it's a nice question like SUVAT, don't bother with it. Most people love SUVAT. You want to be doing the horrible questions that you don't like to do. Okay, graph for intensity for a diffraction grating. I think for an, am I right? So for a diffraction grating, I suppose with a diffraction grating, it's a bit more like this, isn't it? Okay, sorry, that's a bad one. So a double slit tends to be like this. There's this kind of sort of narrow bit in the middle, and it's a bit like that. So that's more like a double slit. If you've got a diffraction grating, which has got lots of lines, you tend to get a lot more light coming through, and you get like something a bit like that, don't you? Is that right? So that's more like with a double slit, because there's only two holes for the light to go through, not much light goes through, and you get this kind of fairly kind of narrow kind of diffraction or interference pattern. When you've got a diffraction grating, a lot more light gets through, so you get brighter things and they're further apart. Does that help? Okay, yeah, Bramble, the Lego. Unfortunately, actually, do you know what? I'll show you because I've got a few other bits of Lego that I've got. So this is my collection of Lego. Unfortunately, though, the local Tesco's, which is kind of about 5 minutes away from my office, they keep selling out of this stuff. So this is my collection. I've got a few multiple bits that I actually got. So these things here are kind of spare. So I've got a few multiples of some of them. But this is basically my collection of Alien Lego. And I can't buy any more Lego at the moment because they're not selling it in the shop, because I think it keeps getting sold out. So I do go back every day, hopefully. What paper should you do if you've done mostly AQA? So I would say, in terms of the papers that you could be doing, I think most people here are doing AQA. I think another good one would be OCR specification A. Don't bother with OCR specification B, it gets a bit weird and difficult. Sorry for the OCR B people watching. Also, you've got Edexcel. You've also got Edexcel International A-Level. And these questions are really similar to those. So if you're doing Edexcel, then IAL papers are really good. It's pretty much the same physics, but actually often the English is written a bit more simply, because a lot of people are doing it with English as an additional language. There's also, I think, paper 3 and paper 6, which are very much focused on the practical skills. And these are really good practice for AQA paper 3A, because there's lots of kind of practical questions. How do I relate lambda mac to the HR diagram? Lambda max. I reckon on an HR diagram, you're going to have a shape a bit like this, and effectively across here we have the colour. So you're going to have like white over here and red over here. So this thing here is going to be related to the colour, and that colour is going to be related to the temperature, and that's then going to be related to lambda. And there's this kind of t squared is proportional to lambda, isn't it? So does that help? I'm not sure. Okay, I reckon I'm going to hold it there. Hopefully all of you are doing okay. Now, don't forget, what was that sound? That's just me going, Rah. Okay, so I reckon that is enough revision for tonight. We're going to do more questions tomorrow. It's going to be a similar format. You know the score. And I reckon for all of you, the best bit of advice I've got is just to keep going through past paper after past paper, and maybe have a folder or a separate piece of paper where when you're marking your paper, if there's something that you're not sure about or something you learned from the mark scheme, use it and write it down so you don't forget all of the lessons you've learned from that paper. So it might be the definition that you weren't sure about. It might be something that you realise that there's an easy mark that you missed out on, and basically have a folder with a couple of bits of paper that has all of the kind of the notes specific to that exam paper that can help you as you're revising. Okay. When workbooks 4, 5 and 6, book 4 is available. You can find it on Amazon, so that's been available and that's already out. Books 5 and 6 I'll be working on from July onwards after the exam season this year, so I'm just going to be sat there doing lots of practical videos and writing workbooks. But yeah, basically book 4 for my daily workout series, perfect for anybody in year 12 at the moment. These are currently available, and if you buy it today, you'll probably get it on Thursday this week. Oh yeah, by the way, Ritrak Gossain saying, yeah, click the like button. Thank you very much, everybody. Yeah, keep liking the videos, keep sharing it. Also, if all of you, could you ask, and please, this is something that you can do, could all of you ask your teachers to buy a school subscription to A-Level Physics Online? That allows me to keep doing what I'm doing, and if your school has a subscription, it means that you don't need to pay for access to all of my extra videos on my website. So ask your teachers to buy a school subscription and tell your teachers how useful my channel has been, and that means hopefully the year 12s coming through and the year 11s doing GCSE, they can actually access all of my videos as well. So please, ask your teachers, just email them saying you should get a school subscription to A-Level Physics Online, and it's basically your student voice which really informs teachers so they use their science department budget wisely. And some of your teachers ask you to buy it instead, which is obviously great, but it's often a better deal if your school buys it because it's a lot cheaper per head. Okay, thank you everybody, and good night. Thanks.